Okay, hey guys, this is Mr. Krieger. This is going to be AP review number 3, the binomial distribution. This will be video 1 of 2. Okay, so print up the lesson. So, if you remember, the binomial distribution was the basis for anytime we did categorical variables when we were doing confidence intervals or hypothesis testing involving proportions. That's where this had come in. Plus, there's other kinds of problems that you need to know how to do. So what is a binomial situation? Okay, here are some examples so you can appreciate it. We use a coin to see which of two football teams gets the choice of kicking off or receiving to begin the game. A basketball player shoots a free throw. The outcomes of interest are she makes the shot or she misses. A young couple prepares for their first child. The possible outcomes are a boy or a girl. A quality control inspector selects an automotive part coming off an assembly line. He is interested in whether or not the part meets the production requirements. So these are the 4 things you need to make sure of in order to know that you have a binomial situation. So there's only 2 categories, success or failure. It doesn't matter how you define success or failure, it's just that one of 2 things could possibly happen. There are a fixed number of observations. For example, we might when we shoot basketball free throws, we might decide that we're going to do 10 shots. Each observation is independent of each other, which means the probability, and it's kind of related to the next one, the probability is the same throughout, okay, the entire event. Okay, if the data is presented via a random situation, then the number of successes is called the binomial random variable, and the probability distribution is called the binomial distribution. Okay, let's start taking a look at some examples. Okay, so let's see if this scenario meets the condition for being a binomial distribution. Blood type is inherited. If both parents carry genes for the O and A blood types, each child has a probability of 0.25, 25% of getting 2 O genes, and so of having blood type O. Different children inherit independently of each other. The number of O blood types among 5 children of these parents is the count X of successes in 5 independent observations with probability 0.25 of success for each observation. So X has the binomial distribution with 5 trials, probability of 0.25, and you can represent the binomial distribution if it meets it this way. B for binomial distribution, 5 is the total number of trials, the n value, and that's the probability of success. Let's make sure we meet the criteria. The first criteria, is there a success or failure? Yes, success or failure here will has blood type O, has type O, or does not. So those are the success failure. Is there a fixed number of observations? Yes, 5 observations. So it's fixed. Are each independent of each other? Well, it says it here. The children inherit independently of each other, so one is not dependent on the other. One will not affect the probability of the next happening. And the probability, so we could say yes, independent. And finally, the probability of success is always the same, 0.25. Constant probability of success, which is in this case 0.25, so it meets the requirements. So let's take a look at a few examples to see if the requirements are met in each of these cases. Deal 10 cards from a shuffled deck and count the number of red cards, where X is the variable that we're talking about. There are 10 observations, and each either gives a red or a black card, and success is a red card. Okay, is this a binomial distribution? Why or why not? You could pause the video to think about it for a minute. Okay, so anyway, the problem here is that they're doing 10 things, so that we're having a fixed number of observations, 10, right? We don't know what the probability of success is, but let's say it's talking about how many red cards there are. Let's say we know how many red cards there are. Let's say there's 4 red cards in a deck. The probability is they're not independent of each other. You're not reshuffling this deck every time. You're shuffling it one time, and then you're dealing out the cards to see how many red cards there are. So this fails. This fails because probability of success changes since each trial is not independent. There's no independence here. So you couldn't use the binomial distribution for this case. So let's try another one. Polling a jury pool. The pool of potential jurors for a murder case contains 100 persons chosen at random from the adult residents of a large city. Each person in the pool is asked whether he or she opposes a death penalty. X is the number of people who say yes. Okay, let's think if this meets the condition for the binomial distribution. So we're picking 100 people, so there's a fixed number of observations. We don't happen to know what the probability of success is here, in other words, finding a person who opposes a death penalty, but assuming that we could figure that out, when we don't know it, sometimes they use 0.5, which I have a question about whether you should do that or not, whether you should use 0.5 as a proxy, but you should, but it could be a fixed amount. We just don't happen to know what it is, so that's going to be the problem. And we're, again, each one is independent. And since we have such a large pool, you know, it's a large city, so there could be, you know, millions of people in the city. So we have independence, and the probability of success will be constant because of such a large pool. It's practically infinite. So as long as we knew the probability of success, I think we could continue on successfully here. Okay, let's look at the next problem. I'm not going to go through all these problems. I'll give you a key so that you could see like what my answers are for these, but you could try these yourself and make sure you understand how to do them. All right, now how do we actually do the binomial like probability? This is the formula. I know it's a little bit weird, but let's talk about what each of the, first of all, I'm going to rewrite this because I happen to like the notation that has NCK and then p to the k, and 1 minus p to the n minus k. We've gone through this in class. Obviously, when we did this very lesson, let me refresh your memory. We want to get, let's say, you're doing 10 free throws, and let's say you want to see what the probability of getting 7 out of 10 incorrectly is. 7 out of 10 shots in, free throws. So this is going to be 70%, and you want 7 out of 7 in. So 70% and 7 in, and this is going to be 30.3 or 30% and 3 in. So that's basically saying you're getting 7 free throws in a row, and then you're missing the last 3, but why does it have to come up in that particular order? This notation rearranges all the possible ways you could get 7 foul shots in and 3 foul shots not in, rearranging them like, for example, you make the first, you miss the second, you make the next, make the next 6 and miss the last 2. That's one possibility, and this will take into account all the different possibilities, all the different combinations of that. So this will be every possible way that could happen, and will give you the probability. You don't really need to know this formula. You're not normally going to be able to need to compute it. You're going to be able to use your calculator to do the computations, okay? So let's take a look at an example, see how, I should tell you what everything stands for. N is the number of trials. They're shooting 10 free throws, so N would be 10. K here would be the number of successes we want, okay? So if we want 7 free throws, and this is going to be 7, and the 7 is going to go there. And P represents the probability of success. Sometimes you could use Q to represent the probability of failure, but 1 minus P is the same thing. You know, like if success is 70%, then failure is 1 minus 0.7, which is 0.3, 30%, okay? Let's try a problem or two. Okay, so inheriting blood type. This is the problem that we were doing before. Let's actually do it. Let's see how to use the calculator too. Each child born to a particular set of parents has a probability of 0.25 having blood type O. So that's our p-value, 0.25, which means Q is 0.75. Okay, if these parents have 5 children, so that means we're going to have 5 trials. We want to find out the probability that exactly 2 of them have blood type O. So this is the binomial distribution. If you go to your calculator, if you go to your second VAR's distributions and you go to binomial, you don't want to go to CDF, you want to go to PDF because this is a fixed number. We want 2 successes out of 5, and then we're going to put in, we have 5 trials, probability of success is 0.25. We want 2 children with type O blood type, so that's 2 successes. and we're going to get 0.2637. Probability of 2 type O's is 0.2637. Okay? Follow? Now, this kind of question kind of requires you to understand this notation. So we'll take a look at it, the notation for actually doing the problems here. Okay, let's take a look. If the probability that the Islanders will beat the Rangers in a game is 2/5, which expression represents the probability that the Islanders will win exactly 4 out of 7 games in a series against the Rangers? So we're assuming that every time they play, the probability that the Islanders will win is 2/5 or 0.4. All right, so this can't be it because we need to take all those rearrangements. Now, we're playing how many games? 7 games, not 5 games. So it's got to be 7 games. We want the Islanders to win exactly 4. So this looks good. So now we get 2/5 to the 4th power, 4 successes. But this is the probability of success. We wouldn't use it again. It's going to be failures to the 3rd power. So there's basically 4 successes, 2/5 is 4 successes, 3 failures, that's a probability of failure. So it has to be this choice, okay? Okay, we'll do 2 more problems. Okay, Mr. and Mrs. Doran have a genetic history that the probability of a child being born to them with a certain trait is 1/8. If they have 4 children, what's the probability that exactly 3 of the 4 children will have that trait? Please try that on your own. So again, I'm going to show you with the formula what it's going to look like. N, P, Q, and K. They're having 4 children. The probability of having that trait is 1/8, which means the probability that they don't have the trait is 7/8. And we want them to have exactly 3 to have that trait. So we're going to do the 4C3. Out of 4 children, 3 of them, we want to see if they have the trait. Probability of success is 1/8. So we're going to have 3 successes and that many failures, 1 failure. We could put that into the calculator. You could just if you want to see where to get that 4C3, it's also in the calculator. Let me show you both ways here. If you go to math probability, or actually before you do that, you got to put that first number in. You do 4, then you go to math PRB, and you do NCR, and you put in 3, and that actually equals 4. Now 1/8 to the 3rd power, is 0.00195, and I'll put 7/8, by the way, is 0.875. Let me multiply this all together. So 4 times I'm actually going to just do this. 4 times, I'll scroll up to here, times that, times 0.875, 0.0068. They have a very small probability that 3 of the 4 children are going to have that trait, because that trait is a rare trait anyway. All right, let's try. Oh, and I'll show you the other way to do it. See, we got this answer 0.0068. Let's see what happens if we use the distribution. Again, here we're going to go to the binomial PDF. We're having 4 trials. 1/8 is 0.125. And we want 3 of them. Let's see what the answer gives us here. Look at that identical, 0.0068359, exactly the same, all right? All right, one more time, we'll do another problem together. You could try it on your own. If the probability that it will rain on a given day is 60%, find the probability it will rain exactly 3 out of 7 days. So again, N, P, Q, K, have 7 days. Probability that it will rain is 0.6, that means the probability it won't rain is 0.4. And we want exactly 3 successes. Putting that right into the calculator, second distributions going to the binomial PDF. We're doing 7, 0.6, and 3. If you're going to do it this shortcut way, you want to write down what you did, binomial PDF, and put in 7, 0.6, 3. This is how you could do it. You're allowed to just write this right onto your AP exam. And you got 0.193536. That's the probability. This is the first video of the 2. Before I go on to the second video, though, you're welcome to try these 2 problems. which I will not be doing now, but I'll send you an answer key to this, and then I'll see you in a minute when I put up the next key.